Hello everyone, I am Radha Kumari Pani, Assistant Professor at VIT. I hope everyone is good. So in last class we have discussed about the thermodynamically parameters, okay, and the relation among them like enthalpy, okay, and internal energy and Gibbs free energy, and the relation with specific capacity, heat capacity Cp and Cv, like dH is equal to Cp dt and du is equal to Cv dt, and H, that is the enthalpy, it is the summation of internal energy and work is done by the system, like H is equal to E plus Pv, and like that G, what is Gibbs free energy and how it is related to temperature and entropy, that is G is equal to H minus Ts, and also the Helmholtz, okay, and all these are the thermodynamically like energetical term, like enthalpy, Gibbs free energy, internal energy, all this. So today let's start with the another interesting parameter, that is entropy. In short words, we can say what is entropy. Entropy means nothing. It is like the uncertainty of the systems, or we can say the disorderness of the system. Let's take one example between solid, liquid and gaseous compound for the better understanding of entropy. What is entropy? Okay, here I am drawing. Let this is solid compound and let this is liquid compound and let this is gaseous or gas compound. And in solid compound, the atoms, okay, the atoms are compactly bonded to each other, okay, we cannot separate easily. In solid compound, the compartment, okay, they are closely packed, but in liquid somehow there is some distance between the atoms, okay, reciprocal to solid, somehow there is some distance between atoms and atoms in the liquid compound. But in case of gaseous compound, the distance, okay, the randomness of the atoms is more, like we can say like this, they cannot be stored like in a compartment, because the disorderness or the randomness or the uncertainty is more. So that we can say the entropy, let S for the solid is less than liquid and is less than entropy of gas. Means from this relation we can see the entropy of gaseous compound is more than that of liquid than that of solid, because in gaseous compound the uncertainty means the disorderness is more, so the entropy is more. That is, we can say entropy is nothing but it is the disorderness of any system, okay. So in thermodynamically, we can say the entropy of any isolated system means there will be no absorbance or no evolution of heat. Okay, there is a closed system. The entropy will always increase. Anyhow, it is isolated or it is closed system or open system. The entropy will always try to, like in positive side. Entropy will always try to increase, because in this universe, okay, this universe is an expanding phase, okay, so the entropy also expanding, the entropy also is an expanding quantity that will increase. Next, why entropy, why this parameter is necessary in thermodynamic concept and how it is useful, okay, how it is useful to derive the energy, that is Helmholtz energy or free energy, that is required for a system to do some work, okay. So this entropy term is like important parameter to derive an internal energy of the system that is useful, needful to do some work. So we can say, we know from the second law of thermodynamics, the entropy will always remain same or try to increase, okay, from the second law of thermodynamics. You know the ds is equal to dq by dt, that formula. Now let the system goes from equilibrium 1 state to equilibrium 2 by changing some infinitesimally small amount of heat, by gaining or by changing small amount of heat. Let the system is growing from system 1 to system 2. Then how we can calculate the entropy change? Let S1 is the entropy for equilibrium state 1 and S2 is the entropy for the equilibrium state 2. So the difference of entropy, that is S2 minus S1, from the second law of thermodynamics, you remember, that is del Q by T by taking the integration from equilibrium state 1 to equilibrium state 2, this equation. So now we know the value at 0 Kelvin, the entropy is 0. You remember that is the fourth law. As for the pure element, that is for entropy at 0 Kelvin, that is 0. We can say that is the reference state for entropy. So the entropy at any temperature, that is St, we can calculate by using this formula. St is equal to integration of del Q by T from 0 to T. So previously we know from the last class we have know the relation, that is enthalpy is equal to E plus PV. Okay, and by deriving we got del Q is equal to dH. From the last class we have derived that del Q is equal to dH at constant pressure. Okay, and also dH is equal to Cp by D. So in place of del Q we can write here 0T. In place of del Q we can write what? dH by T, and in place of dH we can write Cp dt. So the new equation will be 0 to T Cp dt by T. This is the new formula for St. We can write integration of Cp by T from 0 to T, also dH by T from 0 to T. So now sometimes the value of entropy at 298 Kelvin, okay, that is the reference temperature 298 Kelvin, we can calculate by putting St is equal to del S 298 to T, that is Cp dt. The equation is like this, del S 298 plus the temperature 298 to T, here it is Cp dt by T. So we can calculate the free energy at any temperature, that is Gt is equal to Ht minus Tst. Okay, the formula we know for the free energy, G is equal to H minus Ts. So at any temperature Gt is equal to Ht minus Tst. So here now Ht also from the last class we have derived, Ht is equal to H0 plus Cp dt 298 to T. Cp, yes, Cp dt. Ht is equal to H0 plus Cp dt integration 298 to T Kelvin. So in place of Ht we can write, here it is H0 or del H 298. Okay, del H 298. Here it is Cp dt. Like temperature limit will be 298 to T Kelvin minus Tst. In place of St we can write this equation. Okay, T in place of St we can write del S 298 integration 298 Kelvin to T Cp dt. But we know that for the pure element, in pure elements H will be 0. We know that del H 298 for the pure element at temperature 0 Kelvin, the value will be 0. So Gt will be Cp dt 298 to T minus T del S 298 plus Cp dt by T, and the limit is 298 to T. Okay, so here one term is equal, that is specific heat Cp. What is specific heat can be expressed from this equation, A plus B minus C by T square, where A, B, C are the constants. Okay, so the specific heat in terms of empirical formula, this in terms of empirical formula can be expressed, and the specific heat changes with the temperature like this. It will be increase specific heat. Okay, it will with temperature it will increase. So see how this entropy term is responsible to calculate the free energy. Okay, by knowing the entropy we can calculate the free energy. If we know all the term, that is specific heat term, also the temperature, what is the temperature, we can calculate the free energy. Now entropy, there is different types of entropy is there. Okay, by, see, different processing, we got the different entropy by, like in thermal, what is entropy for thermal, entropy, what is entropy for configurational, what is entropy for vibrational, like this translational, rotational, all this. First, what is thermal entropy? So the entropy change due to some changing some temperature, okay, by thermal treatment, what entropy is changing, that is called St, S thermal. Okay, the equation will be del Q by T, del Q in a reversible way. Okay, the S thermal means it is the entropy due to the thermal changing of any system by changing some heat. We can calculate by this formula. So now what is entropy due to the configurational change? Okay, so there is like some one system is there, if you are changing the configuration, then the entropy will be changing. If we are changing its rotational behavior or vibrational behavior or translation behavior, then the entropy is evolved. Okay, the entropy is raised according to the changing of parameters. Like if I am doing some vibrational change in the system, then the entropy is responsible. Okay, that is S vibrational. If I am changing some translational behavior of the system, then the entropy will be S del S like translational. So like this. So total, we can calculate the total entropy for what is del S configurational, del S vibrational, del S rotational, del S electronic, and also del S for nuclear. Any changes we are doing to any system, there will be happening some entropical change. So the net entropy we can calculate by adding all these entropy term. Okay. So now here some beautiful one like example is given for you to better understand how the entropy is changing by changing its configurational change. Okay, let from one in one box 3 blue balls are there. One, see, one, sorry, 1, 2, 3, 3 blue balls, and one here one barrier is there between the two box, and another one box there is 3 red balls are there. Okay, so let they are some in fixed lattice site. If you are changing, okay, if you are we are changing their lattice site, if you are changing their position, so in how many ways, in number of ways, we can change the position of these 6 balls. Okay, in the next slide, see here, beautiful image is given to better understand the number of ways we can change the position of 6 balls. Okay, so these two are, first one and the last one are on mixed test, means there is no changing of their position, like 3 constant, 3 blue balls, 3 red balls, here 3 red balls, 3 blue balls. So in between all these 18, in 18 ways, these two are 1 and 1. These two are constant, okay, on mixed state. But these 18 ways we can change their position of 6 balls. Okay, how? There is one probabilistically term, mathematics is responsible. Okay, so to calculate how many number of ways we can change their position, and the formula is their total 6 balls is there, 6 C3 permutation combination. You remember the formula is, let n r, okay, n factorial r factorial into n minus r factorial. Okay, so 6 factorial, 3 factorial, 6 minus 3 factorial. By doing calculation, we'll get 20. Okay, the number of ways is 20. In 20 ways, we can arrange the balls, 6 balls. Okay. So, here it is written. Let us consider the entropy. Here, okay, the number of ways will be in 20 ways. So, the entropy, there the entropy formula will be there, one formula is there in the next slide. I will discuss. Okay, the entropy due to the configurational changes will be K ln W. Okay, so here K is Boltzmann's constant. Here what is K? That is Boltzmann constant, and the value is 1.23 into 10 to the power minus 23 joule per Kelvin, I think. Okay, this is constant value, Boltzmann's constant, and the W here it is number of arrangement, a number of configurational change. Okay, the number of arrangement, and the formula for calculate, that is combination formula NCR. Okay, we'll put the value omega, and here put the value of kV, that is 1.23 10 to the power minus 20 joule Kelvin. We'll get del S for the configurational. So let's take one example. What is the del S configurational for the pure element? Okay, for pure element, what will be? See here, the formula is there. Let entropy change due to the mixing of two pure elements. If you are mixing two pure elements, there will be some configurational changes. So the entropy arises here. Del S configuration, the formula is K ln W. Okay, and here ln W is the number of arrangement. So W is here NCA, n factorial, n minus n factorial, n factorial. Okay, so if we are mixing two pure elements, what will be the entropy? Same, put the formula S is equal to K ln W. But in case of pure element, there will be no mixed state. Okay, there will be no arrangement. So the W here will be 1. Remember, for pure element, the W will be 1, because for pure element there will be no such like mixed states. Okay, so there will be only one configurational change, only one configuration. So if you are putting the formula here, S is equal to K ln, okay, W, in place of W we can write 1. So we know that ln 1 is equal to 0. So it will be K into 0, entropy is 0. So the entropy for the pure element is 0, because the number of arrangement, the number of configurational changes, the number of mixed states, we can say, is 1. Okay, so it is the formula entropy for mixing of two pure element or two mixed state. What is the entropy? That is Kb ln W. Here Kb is the Boltzmann's constant. The value I have given, that is 1.23 10 to the power minus 23 joule Kelvin, and here W is the number of arrangement we can get from this formula. Okay, so now second, entropy change during melting. Okay, how we calculate the entropy change during the melting process? See, what is melting? Like if you are giving some heat to solid compound, it gains heat. Okay, it gains some heat, but the temperature is not increased. Why? Because the heat it is gained from the outside, it uses that heat for its melting, for its transition from solid to liquid. The heat is stored in this system, okay, to break the bonds of the solid. Okay, it will not increase the temperature of the solid system, but it requires that heat to break the bond in between the solid, so that after that the melting will be happen. And this melting is happening at some constant temperature, that is Tm, that is known as Tm, temperature of melting. And the heat it is absorbed from out source, that is called del H fusion. Fusion means solid to liquid. It's if you are changing from system solid to liquid, the process is called fusion. So the heat absorbed we can write del H fusion, and the temperature is Tm. So by taking this two numerical value, we can calculate what is the entropy during melting. So suppose let's take some aluminum atoms, okay, and it is going in the fusion process, so melting is happening. So how we calculate del S melting? The formula is same, del S is equal to del S fusion by T. How it is? Like from the second law of thermodynamics, del S is equal to dq by T. But here dq, the heat it is in the form of del H fusion. Let in the question there is given for the aluminum atoms the del H fusion. Okay, data is given. The del H fusion is given, that is 10.67 kilojoule per mole. Okay, and the melting temperature, melting point, that is given 933.4 Kelvin. So we have to calculate what is del S melting. Okay, remember one thing, in the calculation part always temperature should be given in Kelvin, or if it is given in Celsius we have to convert to that absolute unit value, that is in Kelvin. Okay, and the unit of del S is kilojoule per mole. So what will be, that is del H fusion by T. So in place of del H we can write 10.67 in kilo means 10 to the power 3 joule per mole divided by temperature of melting, that is 933.4 Kelvin. Okay, so by calculating this value we'll get the value this 11.43 joule per Kelvin per mole is the answer. Okay, only you have to put in the place of del Q, del H is given, and melting temperature, this is melting temperature, it is given. Okay, so we can find out the del H melting. Like this del H melting we can also del H melting we can also calculate the del H for the vaporization. Okay, similarly same formula, del H vaporization means liquid to what, gaseous. So the del H will be del H vapor, and the temperature that is needed for the, that is not Tm, that is T for vaporization. Okay, what is the temperature for vaporization and what is the enthalpy for vaporization? By putting these two value we can calculate the del S for vaporization. So for different like changes, melting or vaporizing, or there is phase changes, there is also we can calculate the del S melting by putting this formula. So this parameter is most important, okay, to calculate the free energy, what is the free energy in the system, and also to know the randomness or disorderliness of the system. So in the next class I will discuss what is like single component system and their free energy. Okay, what is single component system and how you calculate the Gibbs free energy, and how the Gibbs free energy can be calculated by mixing two elements or in the melting state or gaseous state. Okay, so till then, okay, tata, bye bye.